So let's start a new set of lectures called as interfacing circuits. So in the part 1, what we are going to do is we are going to learn about what a synchronizer is and what an arbiter is. Okay. So if you see here, within the motherboard, okay, you have an CPU, and you could have excuse me, you could have n other components which are communicating with the CPU, but they are all clocked by a clocking circuit on the motherboard. Okay, and that is fine. So there is no issues in synchronization. But what about the components which are outside the motherboard? Say for example a keyboard, or for example a mouse, right, and things like that, printer it could be. So they are not clogged systems, right? They are all asynchronous systems. So how do we synchronize that with the with our microprocessors? Okay, although they are asynchronous, okay, there will be some handshaking, right? They'll place some request that I want to send some data. Okay, that is fine. The CPU would recognize that there is a request has been placed, and then depending on the priority of the request, it might give an acknowledgement as and when it is ready to accept the data. That is also fine. Okay, you accept the data. So how do you accept the data? There could be some gate which will open, right, and so that the data can be captured into the microprocessor or onto some register somewhere in the microprocessor, right, or onto the motherboard. Okay, some gate would open and the signal from the asynchronous system will be okay. Now the opening of that gate signal, okay, whenever the synchronous system wants to capture data, that will be clocked, right? So it will be clocked. So when that gate is being opened, okay, there is no guarantee that in the asynchronous system, right, the data will be a 0 or 1. It could be somewhere in between the transition also, because this is not synced at all, right? So that becomes an issue. Okay, so that is the issue which the synchronizer resolves. Okay, it is not it is just because that that data which is in between VIH and VIL and VIH it cannot be accepted by the microprocessor, right? It has to be below VIL or above VIH, right? So that will be resolved by the synchronizer. It will either push the data towards VIH or pull the data towards VIL. Right, so there could be some because of which the error will not be eliminated, but there will be no undetermined state. So that is the purpose of the and that error is not very critical, because you are going to sample this at a very high frequencies. So if one not sample is sampled and it is pushed by the synchronizer towards high or low, and that error is not going to make much of a difference. Okay, so that is what an synchronizer does. Okay, so let's study how it does. Now for example, so this is an back-to-back inverter. It's a simple way of synchronization. Okay, what it does is like you have an data which is coming here. So when the whenever the microprocessor wants to capture the data, it acknowledges the request from the asynchronous system, and it is ready to accept the data. The clock will go high, right? So you will have this pass transistor. Okay, here it is in a clock bar, for example. So negative edge triggered. So you have a clock. When the clock is going low, this data will be captured. So once this data is captured out here, if the data is 1 or 0, or if it is less than VIL and above VIL, so there is no issue, right? But if the data is in intermediate position, you have two inverters which are connected back to back. Okay, so this becomes kind of positive feedback network. So you see here, you see the graph. With time, this will start getting slaved either to high voltage or high level logic 1 or logic 0, right? If it is slightly higher than VM, if the V out here, when I am sampling this, it will eventually go to VOH, and if the signal is below VM, eventually it will come to 0. Right, so this is how I am just resolving the ambiguity which is there while I am sampling this signal by using two back-to-back inverters. So is this graph understood by all of you? Yeah, is the it's a D latch. Yeah, it is just an D latch that is being used. Okay, so that this now if you see here, if the signal is close to VM, intermediate signal, if it is close to intermediate signal, then it will take a larger time to get settled here to go to the VAH or when, and if the signal is close to VIL or close to VIH, that means away from VM, it will get settled faster. So you have to judiciously decide this time period. Okay, after sampling, right, after sampling, how much time should you give for this data to be settled, so that this can be further captured into the microprocessor synchronous system, right? So once you sample, you have to if you we have to it can't be done using a simple inverter. The thing is, it will take yeah, I'll tell you why. First of all, this data need to be captured whenever the microprocessor is ready to capture. So there has to be some switch, right? This data could continuously change, but I will enable this signal into the system only when there is an acknowledgement signal from the microprocessor. One. Okay. The second more important issue is, suppose the signal is out here. Right, if you are giving it to the inverter, it would take a very large time for it to go here if you are using a single inverter, whereas this is like a positive feedback network, right? So the switching will be much faster. You will be shocked, it will be at least 10 to 20 times faster if you have a feedback network like this, right? Because a small increase here will cause a decrease in voltage here, that decrease will cause increase here. So this is like a positive feedback network. It becomes metastable. That means it is these states. Okay, it is going to be this is a bistable latch. It can remain stable only in either 0 or 1. So this back-to-back connection ensures faster switching. Is it okay, Ritu? Yeah. Okay. So let's move forward. Okay. Now, yeah. Okay, now if you see, this is the input signal. Okay, so here the input is 0, here the input is 1, and we are going to sample the signal. So what is this? So this is one transition from low to high till high. So let's concentrate only on one particular transition. Okay, in this transition range, what are those signals? Signal level range which is problematic for us, I mean which can cause undetermined state in the microprocessor. Okay, it will be from VIH to VIL to VIH, right? So I can write this equation. Okay, if you see here, this is the synchronizer time which I am giving to, that is this time. Okay, this time is represented by capital T here. For T is equal to 0. Okay, so this becomes 1. So you will have VMS getting cancelled, and you have VIL, and output is V0, and here also and if you see, this is 1, so VMS gets cancelled, and VIH. That means for T is equal to 0, from the input side, the range of voltages which can cause problem for us is V from VIH minus VIL. So this is the total range of voltages which can cause issues in the next stage. Is this first line clear? How did we get this? Yeah, Sangeet, yeah, is it okay? Okay, so if you see here, okay, I'll just repeat it. Okay, so here in this portion, I am assuming it to be an capacitive charging one. Okay, this equation is like charging a node capacitance. If I see here, because this is like this is coming from an inverter or some static logic, so you can like we saw the delay equations, right, in the VLSI where this is like a delay. This point gets charged, either it goes to 1 through a PMOS and the node capacitance, the load capacitance gets charged. Similarly, if it is going to 0, it is going to get discharged through the NMOS resistance, right? So if you see here, MS is known as the V metastable or the inverter trip point, the exactly midpoint of the VTC curve. Okay, so VMS stands for that. VMS, right? So if it is in exactly at VMS, then even this could get logged, but practically it won't have. Like if you have a VDD 1 and 1, if it is 0.5, exactly 0.5, then there is a small theoretical probability that it can remain stable at 0.5, this horizontal line, but practically that wouldn't happen because of there will be always be some noise. So this curve will get slightly pushed up or down, and then it will reach one of the stable states. Okay, so that is where VM is. Okay, now we are saying yeah, it is VM is the switching threshold. It is the inverter switching threshold. Okay, so now if you see here, at t is equal to 0, if you are sampling it here, right, without a synchronizer, then what is the range of voltages which could cause a problem? From VIH to VIL to VIH, right? Any voltage between VIL, obviously next stage it will be taken as 0, and any voltage which is more than VIH, in the next stage it will be taken as 1. So that is not an issue at all. Only the voltages between VIL and VIH is an issue. So that is what this equation represents, right? So if you take t is equal to 0, so this VMS gets cancelled, so you have the range of VIH minus VIL. So when I am using an synchronizer, okay, what is the input voltage range which will cause an issue, right? If I am using a synchronizer and waiting for 2 toe times, okay, and what is this toe? Toe is the time constant of this input voltage, okay, rise. So because this is coming from a CMOS static logic, so we are assuming there is a time constant at which this can rise and fall, right? So that we have seen in our VLSI classes. Just give me yeah. Okay, is this first equation understood? So if I say if I wait for 2 toe times, okay, so in this equation, if I replace t by 2 toe, this will become e to the power of minus 2. This will also become e to the power of minus 2, right? So again, so you have the only this range of voltages which will cause an issue for me, right? Yeah. So this range of voltages is what does this range signify is if the input voltage is within this range, okay, if I don't use a signal, if I don't use a synchronizer, if the input voltage when the clock is switched, when this is switched on, okay, when I am sampling the signal, if the voltage is within this range, it could cause an error in the reading. Okay, it signifies that. And if I am using a synchronizer, like this, and I am allowing a settling time of 2t, then only this portion of the signal, that is VIH minus VL into e to the power of minus 2, will cause me an issue. That means even if the signal is below above VIL, right, slightly above VIL, it will not cause me a problem because there is a synchronizer which will pull it down to the required level, right? Is it understood now? Yeah, Amar. Tau out here, okay, this tau comes from the RC time constant of the previous stage, how fast the signal is going from 0 to 1 or 1 to 0. how is the, this is an basic, this equation is basic capacitor charging equation, right? The voltage across a capacitor, this is the equation, right? This is the final voltage minus initial into e to the power of stored T divided by RC. This is the capacitor charging equation, normal what we see in the electrical science. Yeah, is it okay, all of you? Okay, so now what you see is, if I wait for 4 terms, so the range of input voltage which will cause a problem will further decrease. That means if I am employing a synchronizer and I keep waiting for a longer time, then this is exponentially, the range which is going to cause problem is decreasing exponentially. Isn't it? That is logical, right? You have an synchronizer out here, and if you don't have a synchronizer, any voltage between VIL and VIH will cause a problem. If I have a synchronizer, then if I wait for a larger time, even if I wait for this much time, even this small, only this small variation of signal which is closed will not get resolved, and all these signals will obviously get resolved by that time, right? So the input range which can cause a problem is exponentially decreasing as we keep waiting in the if we give large waiting time to the synchronizer, right? Is it? It's a very logical thing, right? Okay, so this is how a synchronizer works like, right? Has this impact on the maximum clock frequency, right? Okay, sampling, see these are only within few picoseconds it will settle, right? So you can say, as of now with the present technology where it is in gigahertz, and so this gets settled within few picoseconds, so that is not a major issue. Okay, within gigahertz. Gigahertz corresponds to nanoseconds, right? So this takes, we are just waiting for a few picoseconds time, that's all. Okay. Now if you see here, if you try to find the probability of error, okay, first of all, if you see for one transition from here to here to here, right, what is the voltage input? If I am not using a synchronizer, then the total voltage range is V swing, right? And for a CMOS circuit, V swing is nothing but 0 minus VDD, which is VDD. Okay, so this is a generalized equation. V swing, among the V swing, any voltage between VIH minus VIL will cause like a state which is not desirable. So that is why the probability of like intermediate voltage can be written as VIH minus VL divided by V swing. Is this numerator, this much part is understood, right? The total voltage range, right, which is from V swing from here to here, out of which only this much voltage it will cause me a problem. So in the probability I write VIH minus VL by V swing. Also from in the time domain, from here to here, right, if I assume the rise times and fall times are same in one transition, like if T signal is the time for one transition, okay, one transition means the input has changed from 0 to 1 or 1 to 0, so this much time is the rate at which the input is changing by the keyboard mouse. So this is the total the data is changing here to here, right? So in this time period, only during this time period there could be an issue, right? So again, in the probability, to find the total probability, I'll have to multiply this with TR divided by T signal, right? So this becomes the total probability of an error signal which is sampled, okay, without synchronizer. Is this equation clear to all of you? I can repeat it also. Is it okay with all of you? Yeah, TR is the rise time. Okay, TR is the rise. If we assume rise time and fall time are equal, then TR becomes the rise time, right? So this is the range, which voltage range which can cause a problem. This is the total voltage swing, right? This is the time period which can cause a problem. This is the total time. Okay, you do this, right? Okay. Now if you see here, so number of samples which is sampled per unit time, okay, that will be T. This is the probability. So you got so a number of samples which could be erroneous, okay, which could be erroneous. Okay, now the synchronizer has not been the number of this n sync means average synchronization errors per second, because T5 is the sampling time. If I go back here, this clock period, okay, this clock period. So so let me go. So this, if I divide it by T5, P int by T5, it will give me the average synchronization errors per second. Okay, that is there. Okay, now if I am using a synchronizer, right, I am using sorry, too much of mouse movement. Okay, if I am using an synchronizer like this, we also saw that with the tau increasing, the range of input voltages goes exponentially, right? For 2t it is e to the power of -2, for 4t e to the power of -4. So if you introduce that e to the power of t by 2 out here, okay, that is, if I am using a synchronizer for a waiting period t, okay, which waits for a period t, then the probability of error you got to multiply e to the power of 2 by t, right? And t by 2, where now t is the time period for which it is going to the synchronizer is going to nsync 0 is for t is equal to 0, or you can say if no synchronizer is used. Okay, so that 0 indicates that t is equal to 0, right? So okay, so this is okay, and one more term which we generally use is mean time to failure, which is nothing but 1 by nsync. Okay, now if you see here, if you wait for t, if t is large, then the mean time to failure will be large. That means the time for two failures, okay, between two failures will increase. So it will be much better system. Here also n will decrease with t exponentially. So that is this is how an synchronizer works like. Okay, is it okay with all of you? Then we'll move forward. Okay. Yeah, and then also we have something known as arbiters. Okay, generally when there are a lot of inputs and IO ports connected to an microprocessor, then you have something known as interrupt controllers, right? Where it will accept the request, and based on the priority, it will decide where to give the acknowledgement and all. Okay, that is all. But for simple certain very simple IO devices which are connected with equal priority levels, then you can have a simple circuit which can accept more than one request, and depending on who comes first, the acknowledgement will be given. So it is like both are given equal priority. Whosoever is approaching first, okay, it will generate an acknowledgement signal for that particular request, and it will, and so this is what this arbiter does. Okay, so it is like, if you see here, when both requests are 0, you will find both this A and B are 1. Okay, this is B. Okay, the output of this request to B out here. So both acknowledgement 1 and acknowledgement 2 will be 0. Suppose request 1 arrives first, okay, there is a request signal, it arrives first. So 1 will cause a 0 here, right? So that 0 for this acknowledgement is 0 out here will cause the acknowledgement to go high, right? And also that 0 will come out here and prevent this inverter going from high, because there is no VDD available here. And also that 0 is placed to the input of this NAND gate. So even if the request to becomes high, that will not be processed. So this cannot go to 0, because you already have a 0 out here. The same is true if the request 2 comes first, then that acknowledgement 2 will go high, and and then the request 1, even if it comes, whatever comes later, that will not be considered unless that request signal goes down again. So this resolves the priority. Whosoever comes first, his acknowledgement will go high. Okay, so that is what this circuit does. So in case both of them come together exactly at the same time also, still in this case you will see this is an NAND gate, and they are cross coupled, so it will be a metastable state, right? Metastable means it is highly this can actually be stable only for 0. It can't have 1 here, right? They are cross coupled, so whichever picks up slightly more than the whichever signal starts falling, so there will be a positive feedback, and it will then move and come into a stable state. So that intermediate state is a metastable state, and which is not stable actually. A small disturbance will slave it either to the 1 side or 0 side. Okay, so is this operation clear to all of you? It is just generating the first come first serve basis, and it will create the acknowledgement signal from the request inputs. Okay. What is the application is, suppose there are a few IO devices which are connected for a very small system, and say wherever there is a request placed, so for the same resource, right? And if there are two chaps and say two cores want to accept the same memory, so there will be some arbiter, so it will process the request 1 from 1 core, okay, and it will give that data to that and then when that acknowledgement signal goes, then obviously the data will be enabled, and that based on the acknowledgement, and that core will accept that data, and subsequently once it is accepted, the request signal will go down, and then the second chap who has made a request, the data will be given to that. So if the resources is both two chaps are trying to access the same resource, so you have to have either you have a priority controller in between, or you could have for simple circuits and simple applications you can have an arbiter also. Is the responsibility of the device to raise request again? Yeah, it is one who wants the data, he will raise the request, right? And the arbiter will say, okay, I am ready to provide you the data through an acknowledgement signal. Yeah, so this is what how it works like. Okay. This timing diagram. Oh, okay. This timing diagram is nothing but it just shows that if there are two signals which is exactly going on the same side, right? In this particular case, you will see that the A is it's not that very visible, but A is falling slightly faster than B, so it says it will slave down faster to 0. If there is a small gap in the response of the A and B, because it is a metastable state, this is a cross-connected inverter, so there will be a positive feedback, and it will finally settle down towards A. So whichever node goes 0 in a faster mode, so that will get responded fast, even if the input signals is fast. Okay, that could be because of even stray noise also. What if both are going high, then for sure I can't say either A will be acknowledged or B will be acknowledged. So whatever, because of stray signal, whatever goes slightly higher, so because it is a positive feedback, it will not remain at an intermediate state for long. Okay, it like we saw in this case, it will get slaved to one of the places. Okay. No, this is not an self-timed circuit. Even in the clocked circuits also, they request and acknowledgement and handshaking signals. Yeah, like you said, there will be handshaking signals in asynchronous clocks. Surely there has to be even for synchronous systems also. If there are two synchronous systems which want to access single source, like so for example, your two cores of your CPU are doing certain computation, but they want to have some data from the memory from the same location. So they will have to also, both of them cannot simultaneously read data from the same memory location, right? So in those cases also there will be some arbiters when a source is being shared by more than one processor. So these kind of things, even though they are clocked also, still these arbiters kind of things, they come in play. Okay, let's move forward.